Waiting for another 10 minutes for fixing this AV issue. So today's session is going to be around serverless AI inferencing with Python and WebAssembly. So we'll, of course, talk more about how generative AI ecosystem itself has taken up all and has become a huge part of our lives, but in general also extending that into how can we run inferencing for large language models in a more cost-effective and in a much quicker manner. Because as you might imagine that these large language models are fairly expensive to run, and especially the infrastructure that you typically use in order to do inferencing or even training with these large language models typically requires you to have a huge cluster of CPUs, GPUs, depending on the type of model that you're running. So all of this adds up to the cost and also adds up to the time that it actually takes to execute these large language model based applications. So we'll see that how do you do it in a more cost effective and as well as in a more universal manner where you don't have to worry about what operating system you're running your application on. So we'll be learning all of that today. A quick introduction about myself. I'm Shivay. I'm from India, so I flew in over here, especially for PyOhio. So I'm super grateful to my company, Pieces for Developers. It's a generative AI tool that is essentially helping you with productivity. So if you are, if your company is not willing to use something like a ChatGPT or a Gemini, where you're of course supposed to send all of your personal data, so Pieces for Developers allows you to run offline or open source large language models like Llama 3, Llama 2, Gemma models directly on device, and all of that inferencing actually takes place on device. So it's more privacy focused, especially for companies or individuals who don't want to send their data and still want to use capabilities like having a Copilot app inside of your Jupyter lab or inside of anywhere else. Apart from that, I'm also CNCF and WebAssembly Edge ambassador. So, of course, just want to give a quick introduction about what my company does. As I mentioned, that Pieces is an AI developer tool, and you can leverage it whether you want to manage multiple code snippets, or even if you are like working on a data science project inside of Jupyter Lab or VS Code, you can leverage the offline first capabilities of the LLMs provided, and you can chat with it completely offline. No data is going to be sent to the cloud. But thanks to Pieces for supporting my travel to come all the way from India over here. And I'm super excited to be presenting today. So of course, as I mentioned during the prelogue, that we are in a space today where there are so many Gen AI tools that are out there. And we are essentially seeing the adoption of generative AI with the help of these large language models in every single tool that you can think of, right? Whether it's all the way from using your G Suite of applications, or if you're on the Windows or the Microsoft side. So you'll see adoption in every single application in some or the other form, whether it's through an interactive chatbot or it's through generation tools, because generative AI, of course, means that you can generate images, text with it, like multimodal capabilities. And of course, the crux behind all of this is large language models, which means that typically these are, of course, if you look at just the AI landscape in general, we all start with the most basic neural networks. And these large language models are nothing but a very complex structure of these neural networks. That means that you require more amount of compute, like GPUs and CPU compute, to be able to actually run these AI applications powered by these large language models. And that does come with an additional cost, which is the infrastructure cost. Because now, normally, if you look at a basic Django or fast API application, you could just simply run it inside of a serverless environment or even on a VM without having GPU resources. But adoption of these LLMs and being able to use the LLM inferencing does essentially mean that your DevOps teams or your development teams need to understand how do you deploy GPUs. And deploying GPUs itself can be very tricky, because if you don't use GPUs in a more effective manner, that can add up to your cost, like to your cloud bills very quickly, right? So it's also important to understand that, yeah, while these large language model tools are great for being able to build applications, it's equally important to note that we want to ensure that we can do it in a more cost-effective manner. So that's why today I'll quickly introduce what's WebAssembly. For those folks who don't know what WASM or WebAssembly, you kind of use it in different formats. Now, the boring answer to this question would be that it's a binary instruction format for a virtual device. But it goes much beyond that. So originally, WebAssembly was a technology that was born for running web applications. So as we might know that on the browser, you typically run JavaScript. But if you want to run some other programming language code inside the browser, your browser will simply not allow it. And why? The reason, like why should you actually do that or consider doing that? So if you look at JavaScript, while it's a very great versatile language, it does have its limitation in the fact that it's not very effective when it comes to very compute intensive tasks, such as being able to do AI inferencing or things like video processing. So, for example, Figma or even Adobe, they use WebAssembly to port over C++ code that can run, that gets compiled into this WebAssembly module, and then it can interact with the JavaScript in your browser to do that more compute-intensive tasks for you, whether it's AI inferencing on the browser or being able to do things like video editing. So in-browser video editors, if you have ever used one of them, or even if you have used like Adobe in the web browser or Figma, they are leveraging packages that have essentially ported over C++ code into the browser. And of course, there are a lot of great WebAssembly strengths. The first one being the security sandbox. So the basic principle being over here that WebAssembly itself cannot really do anything on its own. It runs in this kind of sandboxed environment where any calls that have to be made externally, you have to explicitly define how those calls are being made. So it's just running in a more secure sandbox environment. And the best thing that it's actually completely cross-platform and cross-architecture. That means that same WebAssembly module can basically run in the browser. It can run inside of the cloud, inside of serverless environments, and inside of macOS, Windows, any sort of embedded system architecture that you can think of, that same WebAssembly module will run over there. So imagine that, of course, typically when you're having something like a Rust code or you're having a Python code, you compile it into the Rust binary. But sometimes it might be limited based on the system architecture. So, of course, a lot of the WebAssembly ideas come from the fact, like, for example, JVM and how JVM tried to be this true world-class platform. But, of course, we know that JVM is limited to being able to only run Java applications. And given the fact that it runs at near native speeds, it is not like a true binary. So, of course, the speed at which a WebAssembly module will infer is not going to be anytime matching a native binary. But, of course, you get the benefits of being able to be cross-platform. So there is a bit of hit that you take in terms of speeds, but it's still near native speed as compared to a binary as well. And it can, as I mentioned, it can support multiple languages. So, of course, if you look at the entire Python ecosystem, since we are at a Python event, right? We're at PyOhio. So, of course, the landscape for Python and WebAssembly has drastically improved or increased over the past 3 to 4 years, thanks to a lot of work being done on the CPython side, which allows you to actually take CPython code and compile it directly inside of WebAssembly. And for that, if you are interested in learning about that, there's this really nice talk by Katie Bell at PyCon Australia just last year. It has also probably like 60,000 views, one of the most watched WebAssembly with Python videos. But of course, a lot of the capabilities of being able to actually run Python inside of the web browser have been made possible with the help of the projects such as PyOhio and PyScript. Now, again, you'll find a lot of resources for both of these projects on the web. So feel free to always have a look at that. But we're also looking at improving support for being able to make WASI related calls. So WASI is known as the WebAssembly System Interface, which allows you to interact with WebAssembly outside of the browser. Because originally, as I mentioned, that WebAssembly started as a browser technology, but now you can leverage WebAssembly inside of cloud, inside of Kubernetes, inside of serverless environments, which essentially means that you have to deal with networking resources and even file input-output resources. So that capability is provided with the help of this system interface provided by WASI, which allows you to use your WebAssembly modules outside of the browser environment. And there's this really impressive blog post that came out recently. I'll essentially request everyone to give it a read, because that essentially tells how Cloudflare workers, in case you're not aware, Cloudflare workers provide this serverless environment where you can execute your code through these at these edge locations if you're using Cloudflare infrastructure. And it's very quick, and it actually is using WebAssembly with PyOhio to create serverless environments. Of course, my talk today is also using serverless functions in Python, but the project that I'll be using is a bit different. But you can always also look at PyOhio and how Cloudflare has integrated Python inside of serverless environments to create truly impressive speeds, right? It's essentially like you can spin up these Cloudflare workers in a matter of a few milliseconds, if not a few minutes. So that's the entire kind of landscape of Python and the entire PyOhio architecture. But today I'll be introducing this open source project called Spin. So Spin is completely open source project. It's primarily a developer tooling that allows you to create serverless applications with the help of multiple languages, because of course the idea is that Spin converts whatever code that you have written inside of WebAssembly. So there is support for multiple languages within Spin, TypeScript, Rust, but there is an SDK for Python as well. So with Spin, you can essentially create these serverless applications right on the go. And the way that it kind of works is that, for example, you bring your entire code with you, and again, it has multiple languages supported, so JavaScript, Python, Rust, Golang. So you just use this command spin new. So it kind of scaffolds a project for you with a TOML file, and then you write your function or your entire application inside of your programming language of choice, and it will get converted into a WebAssembly module. And then you can actually run that WebAssembly module either inside of a Kubernetes cluster, locally if you want, on your device, or even on the cloud. So we will have a much more hands-on demo for this. So if you are not familiar with these commands or what each and every step does, bear with me. I will be showing you during a live demo of how you can create a new Spin project and how you can leverage it to generate WebAssembly applications. But of course, the biggest elephant in this room is addressing the cold start time for AI. So as I kind of talked about before, that while these LLMs and generative AI applications are immensely useful today, right? The biggest issue that we still face is that typically whenever you're shipping applications running in Python with like NVIDIA support or these GPUs, they can create container image sizes literally in gigabytes in size. And just imagine that every time you make a function call, you have to start up these containers. It can take almost a matter of a few minutes in order to actually start these applications and then wait for the actual inference to take place. So you can see that how much time has just elapsed into making a simple call, because you're having to fetch multiple images, and then you have to make your GPU available, and then you can finally make that call. So, of course, I mean, the thing is that there is a lot of flexibility offered by containers, and there is nothing wrong in using them. But if you are running a smaller application that requires you to have very fast compute, then this is not the ideal situation. And that's where we can actually address the cold start times with the help of WebAssembly. So here's a benchmark that I ran just yesterday, comparing how you can run MobileNet, which is one of the most popular AI, not generative AI, but it's a typical machine learning model that does image recognition or image detection. And as you can see, that the amount of time it actually takes in order to do the inferencing with, let's say, TensorFlow Python in a Linux container, which is in, by the way, this is in milliseconds. So it took almost 200 plus milliseconds to do that inference. And you look at Wasm Edge, which is a WebAssembly runtime, with ahead of time compilation, it's less than 50 milliseconds. So you get a performance difference anywhere between 5 to 10 times, right? And here's a clear example of how quick you can actually do that inferencing. And most of it has to do with the fact that whenever you're running your application code inside of a containerized environment, it has that startup time. So with WebAssembly, the idea is that when you're running a WebAssembly-based application, you spin up the WebAssembly module, which takes literally less than a few milliseconds. And then the WebAssembly module will actually have packaged that application code, which will, let's say, in turn, do the AI inferencing. So here, just to, again, make it very clear, is that you're not basically compiling the actual machine learning model into WebAssembly. You are compiling the application code that makes a call to that machine learning model. You're compiling that application code into WebAssembly. So as soon as you package that application code in Python, in Rust, into that WebAssembly module, it will spin up that WebAssembly module, gets created, does the inferencing in a matter of, again, a few milliseconds, and it closes. So it's like, for example, if you're creating thousands of requests, it is creating thousands of these WebAssembly modules in a matter of milliseconds, doing the inferencing for you, whatever application code you have written, it's supposed to do, and it closes. So essentially what this also allows you to do is that, as I mentioned that earlier with CPUs and GPUs, if you're typically using a container and you're running that containerized application on a GPU, because of this cold start time, essentially what happens is that part of the GPU or an entire GPU is just waiting for your application to actually do the inferencing or make that particular call. So what essentially that limitation we are set with is that now you're not completely utilizing your resources in a nice manner, right? Because you are kind of left with this entire aspect of you're not utilizing your system resources effectively. What if with WebAssembly, because it only takes a matter of a few milliseconds, so you can take a fraction of your GPU, do the inferencing using that GPU, and then your GPU becomes free, and it can be used for the next request. So instead of having to wait for your GPU to complete a request for a matter of few minutes or even seconds, you can very effectively use your GPU and run many more requests, and this essentially also saves up your effectiveness of how you use your system resources. And given the fact that there are so many cloud builds that you have to run when running these GPUs, it makes it capable for not only running your software quickly or your AI inferencing quickly, but also in a much more cost-effective manner by using something like WebAssembly. So of course, what we are supposed to do in this case, so essentially there are two different things that your WebAssembly API will provide to you. One is being able to actually perform inferencing itself. So here is an example of how that infer function would look like, where you would basically pass a model inside of your WebAssembly function, and you'll call it to do inferencing, but you can also actually generate embeddings in case you're running a vector search application where you require to generate embeddings and store these embeddings. So you can do both with the help of the WebAssembly component interface. And the idea, again, as I mentioned, is that you basically compile your entire application into this WebAssembly component, which you can run across different system architectures or different CPU hardware architectures. And the host over here is, of course, like the CPU or the particular application where you're running it. And then the guest is the WebAssembly module that will do that inferencing for you. And the question then comes is where you can actually run this spin application. So you can run it on your device locally, you can run it on cloud applications, you can also run it on Kubernetes clusters, wherever you want, with the help of projects like SpinCube. And again, all of these are completely open source. And here's like an example of how you would run it in a cloud environment. So let's say that you have that spin application, you are basically running a large language model. So of course, when you're doing the inferencing side of things, that's running on top of a native GPU. So you can do that inferencing on the GPU. You can also set context, and if you have some embeddings, you can store them inside of a database that's also actually running on top of WebAssembly as well. So all of this infrastructure is basically being run on WebAssembly. So not just the AI inferencing, but if your application has some database, whether it's key value store or also whether you're running some NoSQL data, all of that can be translated into WebAssembly. So specifically when it comes to Python, as I mentioned, that Spin is a universal format. So you can use any programming language and convert that into a Spin project, but there is a dedicated Python SDK. Now, the older version for this used Py2wasm, which is basically based out of CPython. But the modern version of being able to leverage is something that we call as componentize.py. Excuse me if I butcher that name. It's a bit difficult to pronounce. So this is a bytecode alliance project, if you are not aware what bytecode is. So similar to how we have the PSF, which is the Python Software Foundation for Python, we have the bytecode alliance that deals with everything that goes on into the WebAssembly ecosystem and the WebAssembly world. So essentially, this takes your Python code and will convert it into a WebAssembly component that you can then run and infer anywhere that you want. And essentially, the output is basically this WebAssembly component that you can run anywhere. So of course, now coming to the main point, that how can you create your own Python-based serverless AI application, given again considering the fact that serverless functions are a bit hard to run or because of the cold start times as we saw. So the first thing that everyone can do, and of course, I'll be sharing the resources for this presentation. So if you want to try it out, you can go ahead and do it. I'm going to be running the demo inside of a cloud-based GitHub code space, but you can do it in your local environment as well. But you'll be required to do a couple of things. So first thing would be to install Spin. And ensure that you have Spin version 1.5 and above, because that's where the serverless AI capabilities are offered. And you have to install the Python dependencies specifically with the Python SDK. And then you create a new Spin app by using the Spin new command, which will essentially provide you a scaffold project with all of the system dependencies that are required to run your project. And then you create a Python environment, and then you configure your spin.toml file, which is essentially your configuration file, where you mention which particular AI model. So whether it's like Llama 2, Code Llama, or Gemma, you mention that particular AI model which you'll be using for inferencing. So what it will actually do is that it will download the actual model binaries inside of your project and then call that particular model. Because as I mentioned, that with WebAssembly, we are not converting the AI model into WebAssembly. We are leveraging the capabilities offered by the application code, and then we use that to actually call the AI model. And then finally, you can build and deploy your applications using Spin Build and Spin Deploy. And
it is 10:45. We already stopped time. Of course, we got a late start. And the second talk in this track has been canceled. So if you got to go, next talk starts at 11. If you can't stay, that's great.
Yeah. But yeah, I think I'll not take more than 10 minutes more because we started 10 minutes late. So I think we are pretty much on time. And here's like an example of the source code that I'll be showing you that we'll be building. So here what you see is that in the first 3 lines of code, we are importing all of the necessary modules to use the Spin SDK. And then we have a handler class that's essentially just being used for HTTP requests for doing the request and response handling. And here what you'll see is that we are specifically using the llm.infer with options where you of course define which LLM model do you want to use, and then the actual prompt that you want to send to that model, and then some params such as of course whenever you're making an API call to an LLM, you want to basically define what is the max number of output tokens that will be used by the model or the temperature to kind of define how randomized of a response you actually want. And then we are just returning the response. So let's get started. And again, the source code for all of this will be available. So these resources, I'll be sharing the QR code as well. So stay tuned for that. But let's start building now. So the first thing that we'll be doing as we have in the steps over here is we'll be starting or scaffolding a new Spin project. Again, ensure that you have installed Spin. It's supported, by the way, locally. So you can, if you have Mac, Windows, or Linux, you can install Spin anywhere. So imagining that we have Spin installed, I will go ahead and create a new terminal over here. And we'll use the same command that we just saw over here with the Spin new. So in this case, we would basically use the Spin new. Now, one thing to keep in mind is, and I think I should already have this particular command ready. So we'll do Spin new. And then and by the way, let me zoom in a bit more. Is this readable for everyone? Okay, perfect. I can zoom in a bit more as well. So we'll use Spin new. Then I'll give it a flag of -t. So it provides you some templates that you can use directly. So in this case, what we're going to be doing is that we are creating a template for HTTP PY. So it's a template code that is provided to you where you can make simple HTTP requests. So it essentially takes the HTTP paradigm and runs that with the help of WebAssembly. So we'll use the HTTP Py, and then we can give it a name. So I already created one example over here called Hello PyOhio. I can call it probably Hello PyOhio 2. And then simply, if I want to accept some defaults, I can use that flag as well. So I'll say accept defaults. So what this will do is that it will scaffold a new project for me. And as you can see that this is the Hello PyOhio code. Here it has already given me a starter code, which is this just to kind of do basic incoming handler for HTTP requests. So the scaffold project, and then we have this pin.toml file, which has the application code, it has the author, and of course the WebAssembly component defined. So essentially, when you build your application, your app.py is what gets converted into the WebAssembly module, and that WebAssembly module will be this app.wasm that you can see in this example. So we'll see that in practice when we go ahead and run this application. Now, of course, the application code for the one that I showed you over here, which is what we are building, I'll use and I will replace this entire code and I will replace it with our LLM inferencing. And the other thing that we have to do is within our TOML file, we have to define what particular type of AI model we are using. So in this case, I will again just use it from the previous one that we have over here. So in this case, it is going to be the AI model. So I'll be using Llama 2. You can use any AI model that you want. So I will go ahead and add this over here. So this should be okay over here. Yeah. So once I'm done with this, I'm pretty much ready. I'm set with my application code in order to run this. So now what I'll go ahead and do is I'll do spin build. So just now notice that as I do this, the command, one second, no directory. I have to go into my hello PyOhio 2 folder. All right. So now when I do the spin build, notice what command it basically runs. So let me zoom in a bit more. All right, so it says building hello Ohio component with componentize.py. So that's the componentize py that basically takes your Python code and converts that into the WebAssembly module. And as you can see that now we have generated this app.wasm file, and this is what will basically get executed in that serverless environment. Now when I do spin deploy, that is what will basically take this WebAssembly module and run it inside of a serverless environment and which has access to your GPU cluster. In this case, it connects to Fermion Cloud, which is the cloud over here, but you can very easily replace this with your own cloud, whether you're using AWS, GCP, Azure, whatever cloud service that you want. So it's basically deploying this entire code on Fermion Cloud. So if I go to cloud.fermion.com, I should be able to go to my applications folder, and you can see that it is right now creating this hello PyOhio code, and this is the serverless environment that we are running it in. So there's no dedicated like Node.js or a Flask server that's running this. It's as soon as like you make a call to this application, it will create a new WASM module. It will then do the inferencing for you, and it will destroy that WASM module in a matter of a few milliseconds. So we have completed this application, so we can go ahead and open this. So in this case, if you look at the prompt that I had sent it, it was write code to implement an array in Java, C++, JavaScript, and Python. So as you can see, this is the response that it generated. And as soon as so the idea is that as soon as I refresh the application, it is basically generating a new WebAssembly module, creating the response, and then killing the application as soon as it is done doing that inferencing. So that if you're using a GPU instance, as soon as your execution of your function has been completed, now your GPU cluster is available. So I have another running application that I'll quickly show you, which is basically creating sentiment analysis, right? So of course, like sentiment analysis is one of the most commonly used functions. So here in my app.py code, I'll quickly show you. So here I've given a prompt over here where you are a bot that generates sentiment analysis responses. So follow this pattern to give whether you want to give a positive or a negative response. And I'm basically sending that as a sentence. So from my request body, the sentence that I'm giving it, it will basically pass that particular prompt with my given sentence and again do the LLM inferencing for me. So if I want to see this in action, let's go ahead and do that. So here, the way that I have executed, and again, the source code for this will be available to all of you. So here, for example, I'm making a post request with the sentence that I want to run and then the sentiment analysis. So in this case, if I run it, it says it's positive. Let's try to, perhaps change the sentence itself and use something probably a bit kind of a negative connotation. I can say, I am nervous for my presentation. So let's try that out. So I am nervous for my presentation. Let's see if that works. I think something. Yeah, I think, yeah. Let me probably use this again, because sometimes I'm always pretty bad with using the terminal. Let's see. I am nervous to run this application. Let's see if this works. Okay. So it says that it's neutral, because nervousness can be treated as positive and nervous or negative. But yeah, I mean, I hope that gives you an idea. Again, even with this request, as soon as I ran this request, it generated a WebAssembly module connected to that AI cloud cluster where the GPU is running, and the serverless function made the call to the model using the GPU as for inferencing, and then it gave back that response. But essentially, that's what is the things that I showed you. You can check out these resources, by the way, by scanning this QR code. This will give you access to the entire code repository for both of my demos that I ran, but also for the metrics that I showed you on how quick it is actually to be able to run AI applications with the help of WebAssembly. But yeah, I'll be around in the conference today, so if you have any questions, I know we are out of time, but feel free to ask your questions, and I'll be more than happy to respond. Thank you.